So welcome now to your lesson on states and particle theory. If we're going to talk about chemistry, we better know three of the major definitions. The first thing is we have to know what matter is. Chemistry is just studying how matter of one type interacts with matter of another type. So what is matter? Matter is anything that has mass and volume. Well, if that's the definition of matter, then you better know what mass is. Mass is when you measure how many particles there are in an object. It's a quantity. You can measure it in all different types of units, kgs, pounds, tons, or even tones. These are not the exact same thing. They're slightly different measurements. One's imperial and one's metric. You can measure it in ounces. You can even measure it if you're from the UK. You might even use stones for your weight. 1 stone is equal to 14 pounds. So you might say, oh, I'm 10.5 stones, rather than saying that you are in so many pounds, right? So matter is anything that has mass, so it's made up of particles, and volume. The volume is the fact that those particles take up space, okay? So matter, anything that has mass and volume. When we're talking about changes of state, this will make more sense when we do our next lesson on physical and chemical changes, but you need to know that a change of state is something called a physical change. It's written here so that your notes are complete, but I will discuss and explain it in better detail on the next lesson. So you already know what changes of state are. When you have a solid and it melts, you end up with a liquid. When you have a liquid and it evaporates, you end up with a gas. If the gas particles then condense, they become a liquid, and if the liquid freezes, it becomes a solid. Those are terms you've already heard, you've already used. You just need to make sure you know them in the right order. And today we're going to explain why it is that happens. There are 2 terms, though, that you may or may not have yet encountered in your science curriculum. And that's when you go from a solid and you skip the liquid phase. You go from a solid and you jump right to a gas. That's something called sublimation. Sublimation skips the liquid phase and goes straight to the gas. The other direction, going from a gas and skipping the liquid phase to go straight to a solid, is called deposition. And 2 famous examples of from sublimation and deposition is, for sublimation, you could talk about, I don't know if you guys have heard of mothballs before. Mothballs are basically these little stinky balls made of a chemical that bugs, actually humans don't like it either. It stinks really, really bad. And let's say you're storing some clothes up in the attic and you don't want the bugs to get in there and eat through your sweaters over the summer months when you're storing stuff. You throw mothballs in there, and then over time, the mothballs, which are solid, will begin to produce a gas. And it's just the actual solid itself becoming a gas. Never becomes a liquid, so it never wets the clothes. It jumps straight to a gas, and the gas is quite stinky. So bugs don't want to smell that gas, and they'll stay away. Called mothballs specifically because moths used to eat through people's clothes. They used to plant their eggs, and then they would, the little larvae that grows, like the little caterpillars, would come out, and they would eat people's clothing and put big holes in them. And then that would be a big problem. So mothballs specifically were to keep bugs away. There's other examples of solids that jump straight to gases in your home. If you have any kind of an air freshener, like a freshener that kind of seems to disappear over time, it's a solid or like a jelly kind of a thing, but then you come back in a month and that thing has shrunk right down. It never turned into a liquid, it just went straight to being a gas. So air fresheners are good examples of solids sublimating to become gases. If you want a good example of a gas becoming a solid, skipping again the liquid phase, gas jumping straight to solid and depositing, snowflakes are an excellent example of that. So up in a cloud, you have your water vapor, and rather than it turning into a liquid drop and falling down as rain, it goes straight from the water vapor stage and it goes into becoming directly into a solid. It forms the crystal snow and then falls to the ground. So you can skip, you don't always have to have rain and then it become some kind of ice, something falling from the sky. You can go straight to a snowflake from the gas. Please be very good on these terms: melting, evaporating, condensing, freezing, and the sublimating and deposition part. Now, in order to move towards the right, if you want to melt, evaporate, or sublimate, the way that you go in this direction is you have to add energy, and usually that's in the form of heat, because the molecules or the particles that make up this solid need to spread farther apart. And when they spread farther apart, it can become a liquid. And then when the liquid particles spread farther apart, it becomes a gas. In each of these stages, it's still the exact same particles. So for example, let's say we're dealing with water. Water is H2O, right? A couple hydrogens and an oxygen. H2O is the chemical formula for it. So we have solid water, which is ice. When it melts, it becomes liquid, but it's still water. It's still H2O. It's just the H2O molecules are farther apart. And then when it becomes water vapor, it's still water. Steam is still water particles. It's just water particles that are really far apart. They've got so much energy, so much heat to them that they spread out. All right? So in each of these stages, it's the exact same chemical. That's why we say this is a physical change. Physical changes are just changes that happen when you take the exact same particles, but maybe you put them in separate piles, or you move them farther apart, or you move them closer together. So you don't change the chemicals themselves. It's always water every time. So it's a physical change. So change of state is considered a physical change. So if I want to go this way to the right, from solid to liquid to gas, or straight from solid and sublimate to a gas, I have to add energy to get those particles moving and spreading out. If I want to go the other direction, I'm going to have to remove that energy to calm the molecules down. Now, melting point, freezing point, boiling point, condensing point, these are all important terms, but they're not too tough to understand. The melting point is the exact temperature that it takes to have a solid turn into a liquid. So here's your melting point up here on the diagram. So melting point is whatever point it takes to get the solid to turn into a liquid. Melting point for water is 0 degrees Celsius. But the melting point for other substances could be completely different temperature. It just happens to be that water's melting point is 0 degrees. Now the neat thing is that the melting point and the freezing point are the exact same temperature. So in order to get the solid to turn into a liquid, you have to be at 0 degrees. And in order to get the liquid to become a solid, you have to be at 0 degrees as well. So it's the exact same. It's one point or one temperature where either of these things are possible. So what if I gave you solid water and I told you it's at 0 degrees C? It doesn't necessarily have to melt until you sort of kick it over the edge. So if it's sitting right at 0 degrees, it can stay solid. If you already have a liquid water and you're sitting right at 0 degrees, it can stay liquid. What you have to do in order to push it one way or the other is just to change an ever so tiny amount of the energy. If it's sitting right there, right at the melting point at 0 degrees, and you remove the tiniest bit of heat, it'll swing to a solid. If you are sitting there and you add the tiniest bit of heat, it'll swing to a liquid. So the melting point is the point identical to the freezing point. You could tip it in either direction. Hopefully that makes good sense. That's the same thing for the boiling point and the condensing point. For water specifically, the boiling point is 100 degrees Celsius. 100 degrees Celsius. It'll be different for other types of materials. But right at 100 degrees, if you already have a liquid and it's at 100, it'll stay a liquid until you give it a tiny bit more energy and it pushes it over the edge and becomes a gas. If it's already a gas and you've cooled it down to 100 degrees, it can stay a gas until, again, you push it just over the edge and suddenly it'll become a liquid. Okay? So boiling point, condensing point, exact same number. Melting point, freezing point, exact same number. It just depends which direction you're going or what you're going to call it. Every substance has its own unique melting point and its own unique boiling point. If you have just regular pure water, it's 0 degrees over here for melting and it's 100 degrees over here for boiling. But if you were to have salt water, so you added another chemical in there, you added some table salt into the water, the melting point would move over, so that would have to be even colder to get it. So not 0, but colder than 0 to get it to actually become a solid. And the boiling point would be much higher just by adding that other chemical in there, right? So every single substance has its own melting point and boiling point. And that's what we have written here. So if you're melting, solid to liquid. And if you're freezing, it's liquid to solid. Same temperature for both of those. Boiling point, condensing point, liquid to gas, gas to liquid, same temperature. So let's zoom in a little bit then and look at the particles and the heat that's applied then. When you're adding heat to something, you're warming it up, you are adding energy is really what you're doing. And what you're going to do then is have those molecules, which are already wiggling, will start to move even faster. If you remove the heat, cooling things down, you're removing energy and the particles will move slower. And here's an important part of this lesson that you need to commit to memory, and that's discussing the particle theory of matter. You may have heard particle theory taught in elementary school, and here we are teaching it in better detail. It'll help you even all the way up to grade 12 in high school if you can commit this to memory, because it really does explain why chemicals act the way that they act. So the particle theory of matter is used to describe the structure, so how it's put together, what the parts are and how they fit together, and the behavior, what that type of chemical, what that matter will do, those particles will do. So how it's put together and how it behaves. First, all matter is composed or made up of very tiny particles. Those particles are called atoms, and when you attach atoms together and you allow them to share electrons, we'll talk about that in a later lesson, you can form molecules. So all matter is made of very tiny particles, whether it's atoms or the larger molecules. All the particles have some space between them. So even though you're looking down now at maybe your desk or wherever you're sitting at, and you're looking at a solid and you're thinking like, oh no, there's no way for light to pass through that. Those particles are really tight together if it's a solid. But there is actually, if you were to zoom in on the atomic level, you would actually have space between every single particle. Giant gaps of space actually between every single particle. I'll show you that when we get to talking about the structure of atoms. So all matter, very tiny particles. All particles have space between them. Third, all particles are always moving. They are always in motion. They basically vibrate back and forth. Okay? Vibrating. Then we would say that the particles in a substance are attracted to each other. They want to stick together, right? So please commit all 4 of these to memory. Composed of tiny particles, all particles have space, the particles are always in motion, and the particles can attract each other. And here's that in visual form. So here you have the solid, and you can see the particles are much closer together. There is space between if you were able to zoom in even farther, but they're quite tightly packed. And because they're so close to one another, there's strong forces that hold them together. So a solid will stick to the other parts of its solid. As you begin to move the particles farther apart from each other and you give them more of a space, they have less of an attraction or less of a hold on each other. And when that happens, they're able to slide past each other like in a liquid. So they're more spaced out. And then when you put a lot of space between them, they have a very loose hold on one another. They can't hold each other together. And you have a gas that's able to spread out and fill its entire container. Very weak forces because they're very, very far apart. And that, my friends, is the end of the formal lesson. Enjoy your day.